So we've just talked about lines. We're going to be a little bit more general. Today we're going to talk about section 0.2. We're going to talk about functions. Now here's the deal. Anytime you have such as one variable depending on another one, such as like y depends on x for most of our functions, where y is dictated by what you put in for x, some independent variable x and some dependent variable y, we can call that a function. The only thing that you really need to have for a function is that every input has one output, not two outputs. Otherwise, you don't have a function because you plug in a number and you wouldn't know where to go. So when we say a function, we mean some expression where each input determines exactly one unique output. Usually for our inputs, we see those are like x's. So typically that's an x. So some expression where each input, x, has exactly one unique means doesn't happen again, one unique output. And we typically call those y's or f of x for us. You know, we can represent functions a lot of ways, though. We can represent with tables, graphs, formulas. One time I was fishing and I caught 4 fish, and because I'm a math dork, I made a table of it. Because you don't do that? Is that not normal? Anyway, here's one example of a function, a very easy function. Here's my fishes. I think that's fish. Fish caught and the number of pounds that they were. So my first fish, second fish, third fish, I caught 4 that day. First one was 3.2 pounds. Not bad. Next was 1.4, then 2.8, and then I caught a massive bass for 7.3. That was a good day. Good day. Good day. Threw them all back. Threw them all back. Firstly, let's define what the inputs and outputs are for this particular, we're going to see if it's a function in just a second. Firstly, my inputs are, well, the fish that I caught in this instance. The outputs would be, well, their weights when I weighed them, because the scale would be like my function, right? I put my first fish on there, it'd give me a weight. Put my second fish on there, it'd give me a weight. Now, the question is it a function? Is it a function? Does each input, does each fish have one specific weight? Yeah. Okay. You know what? I need to erase something right here. Exactly one, not unique, but one output. Unique output would be a one-to-one function, and we're not there yet. So when we say it has one output, I mean that I don't have fish number 1 weighed 3.2 pounds and 4.7 pounds. Because you'd say, how much did your first fish weigh? I'd say 3.8 or 3.2 or 4.7. Would that make sense to you? Well, no, seriously, how much did your fish weigh? 3.2 or 4.7. And you're like, that doesn't make any sense. You're giving me 2 weights for the same fish. Does that make sense to you? Would that make sense if you asked me that question, how much did your first fish weigh? And I said, oh, well, either 3.2 or 4.7. You said, well, aren't we talking about your first fish? Yes, we are. 3.2 or 4.7. You're like, well, if I'm having dinner with you tonight, I need to know if I'm going to be hungry at 3.2 pounds, or if I'm going to be satisfied at 4.7, I go 3.2 or 4.7. It doesn't make any sense, right? I have to give you a specific weight for that one fish. That's what a function does. It says if you say fish number 1, you're talking about one specific weight. Okay? Maybe I should say the word specific output, not unique, because one unique output, we will be talking about one-to-one in just a little bit. How about number 2? Does number 2 give me out just one weight? Yeah, it doesn't say 1.4 and then something else over here. That would not be a function. So this thing is a function. Any fish that I have, it has one specific weight that we're talking about. If I did this, would it still be a function? Yeah. The answer is yeah. Yeah, it would be a function. This fish 4 weighed 3.2 pounds, not something else. It doesn't matter that these things are the same. That can happen. Let me give you, for instance, as far as a graph goes. That right there, has the same output at several different spots, right? That would be some sort of an x squared. It says if I'm at this point or this point, I still have the same exact output. That's okay. This is still a function. We're going to talk about vertical line test too. It's a function. It wouldn't be a one-to-one function. It wouldn't pass a horizontal line test, but it would be a function. We can also talk about functions. Really, we don't see fish caught normally. We see some sort of function like this, especially if you're doing any mathematical modeling, you might see this, where you have a set of inputs, our x's, you got a set of outputs. That thing would be a function. Every one of our inputs or x's has one output. How you would say that it wouldn't be a function if you came back and did something like this. Would that be a function?
Yeah.
No. No, if your inputs are repeated with different outputs, well then you don't have a function there. So that would be a no bueno. Sometimes we actually have formulas too that are functions. This is a function. What is that, by the way? Sure, and it's a function because if you give me a radius, it's going to give me out one area, isn't it? So our area depends on the radius that you have for your circle. It's not like I say, you have a radius of 3, what's your area? And you give me 2 different answers. That wouldn't make any sense. It wouldn't be a function. The formula would fail. Also, we can have some graphs. Graphically, if we did something like that, we can represent them lots of different ways. Basic tables here, formulas, which we spend most of our time in formulas and graphs. That's another way we represent functions. Just one note, functions have to have only one output for each input. That's the key thing. I hope that you got that from this. Now, one more thing about this one. Let's say we change it just a bit, and we say y equals f of x. Could you find f of 0? What would that mean to do? It would mean, if y is f of x, it says y is a function of x, and I'm asking for f of 0. Can you tell me what is f of 0 in this case? Okay, it is how much? 2, because it says you go over to the input of 0, you look up the output for that particular input. So here it says find your input, remember this is f of x, right? So go to your x, go to 0, tell me what the output is, oh it's 2. How about f of 3? What's f of 3, everybody? That wasn't everybody, well, I'll take it, fine, whatever. Yeah, it just says you go to your input of 3, you find out what that output was. Typically, we'll use this in this type of situation, where you have some sort of equation, y equals 3x squared minus 4x plus 2. The y equals thing isn't always the best for us to represent a function. The reason is because in this class we're going to look at a lot of different functions at once, and you want to be able to distinguish between them. If I have just y equals a function, then y equals another function, y equals another function, and I say, look at the function y, you're going to be like, there's 3 of them, which one are you talking about? We often use this type of notation to distinguish between them. So if I said, instead of y equals f of x, y equals that function, I want f of x, or g of x, or h of x. That way we can distinguish between those graphs and those formulas and these equations. Also, what it lets us do is if I ask you to plug in a number, it will tell you inherently what number you plugged in. For instance, if I say for you here, can you find me f of 0, well, what does f of 0 do? What's that supposed to do for you? Oh, so supposed to plug in, okay, supposed to plug in 0 and find out what the output is. Can you plug in 0 here?
Yeah, 2.
Okay, so, you said 2? Okay, so you plug in 0, 0, yeah, you get the 2. What's nice about this is if you plug in 2 from this one, well, you're going to get y equals 2. But does this tell you what you plugged in to get the 2? No. Does this one tell you what you plugged in to get the 2?
Yes.
Yeah, this actually will give you a coordinate point. It will say you plugged in 0, you got out 2. And that's kind of nice. This is one other reason why we use that function notation. Let's go back to those graphs too. Can you tell what is a function just by looking at the graph? So for instance, for instance, can you tell me whether these things are functions or not just by looking at them? We know we can tell with tables, right? Because if we have an input repeated with a different output, well, that says it right there. We're going to be able to tell formulaically in just a little bit. But right here, just by graphically, what's that thing called where you test a line to see whether or not it is a function or not?
Vertical line test.
Yeah, we have a vertical line test. So imagine, bless you, wow, that was a powerful one. It was like a sneeze grenade going off. Sneeze grenade? That would be so gross. So disgusting. That's where my mind is right now. Okay, so if you imagine every vertical line, it's supposed to touch your graph at only one spot, if it touches at all. So is this thing a function? Yeah, for sure. Every vertical line hits this diagonal at only one spot. So yeah, this is a function. How about that one? Is that a function? Yeah, parabolas are basic functions. Every vertical line hits this. Is it a one-to-one function? Do you know that?
No.
One-to-one function would be the horizontal line test, saying that every input has one unique output. It says it doesn't happen again. This is not one-to-one, but it is certainly a function. How about this one? Is this a function? Yeah, sure. Now, what about this is an interesting case. What about this one? Is this a function? No. Does every vertical line hit the graph at most once? Yeah. Yeah. Now, a couple people get hung up because of, wait a second, don't you have to have something at this point 0? And the answer is no. Not every input has to have an output, but if it does, it only happens once. Do you see the difference there? This doesn't have an output, it's undefined at 0. This would be like 1 over x. But if it is defined, then that definition has to be one exact point to be a function. So yeah, this is still a function. How about this one? No, this fails it, because if you plug in this point, you actually get 1, 2, 3 points out. We can't deal with that. So this is not a function. So vertical line test verbally, I'm not going to write it down because I know y'all know it, says that you imagine every possible vertical line. That vertical lines have to touch every point of that graph at most one spot. So touch the graph at most one spot. It can't ever cross over more than one spot vertically. How many people feel okay with our very quick introduction to functions so far? You having fun yet?
Joy.
Joy, joy? Okay. Well, let's consider one more thing. What is that?
Circle.
Say it louder.
Circle.
Circle. Did you all know it was a circle? Did you read the section on circles like I told you to? Said read circles, right? Did you read circles? Hopefully you read circles. That's a circle. What's it centered at? Centered at the origin. Very good. 0, 0. The way you'd shift circles around, hopefully you remember this from your intermediate algebra days, is you'd have some parentheses in here like x minus h and y plus k. That would shift that around. Okay. What's your radius? Good, because we know this is the radius squared, so our radius would be 5. Is it a function? Is it a function? Why not? Well, yeah, I mean, visually we know it's a circle, right? Yeah. That's circular reasoning, isn't it? Get it? Yeah, thanks. Where's my drums? It's a circle, so it's not going to pass the vertical line test. That's one way we can define it. If we actually graph this, it's a center, 0, 0, radius of 5. It looks like this. It's certainly not going to pass that vertical line test. However, can you see it formulaically as well? Specifically, can you solve this for y and see that this is not a function? Let's try that. How would you solve this for y? What would you do first? Okay, so probably isolate the y. Get the x squared over there somehow. You know you're going to get y squared equals 25 minus x squared. True? Now y is not completely isolated. What would we have to do to get y all by itself? Let's do that. So if we take a square root, of course that means both sides. That's legal to do. On the left-hand side we get y. On the right-hand side, tell me what I'm forgetting right here.
Plus or minus.
Oh yeah. Every time you take a square root of something, you got to have a plus and minus. So if the square root's on your paper, no big deal. But if it's not there and you put it on your paper, like we did up here, right? We didn't start with that square root. We introduced it to the problem. When you do that, you absolutely must have a plus or minus. Do you see the situation now? I want you to try to plug in a number and tell me how many answers you get out, how many outputs you get out, how many you're going to get. Yeah, because if you plug in something like, I don't know, 4, you're going to get 25 minus 16, right? Right? You're going to get 9, the square root of 9.
3.
But then you're going to take plus 3 and minus 3. That's giving you those two answers. As soon as you have that out of a formula, it's not a function. Now the question is, could you work with it to look at parts of this function? And that answer is, yeah, absolutely. If we define this a little bit differently, if we say, well, let's call f of x the square root of 25 minus x squared, and g of x the negative square root of 25 minus x squared. Now let me ask you a question. Is this a function? Yeah, sure. Is this a function? Yeah, together they're not a function, but separately, well, we could talk about each piece. That'd be fine. What would this be, the top half or the bottom half of the circle? Yeah. Top half, bottom half. Then we could talk about them. But altogether, when we look at that thing, certainly we don't have a function there. The other types of functions we need to talk about, one of them is called piecewise functions. Before we go on to that, are there any questions on for the line test or what we're doing over here, kind of just showing that all formulas aren't functions? I mean, we don't have that necessity. And when we solve them, though, we can talk about pieces of them as functions. Are you guys all with me on this so far? You ready to talk about piecewise functions?
Sure.
You sure?
Sure.
All right. Here's what a piecewise function basically. Have you guys seen a piecewise function before? Yeah. Okay. I know you have. You're supposed to have seen it. To be in this class, you've seen it before. One very basic piecewise function we're going to deal with in just a second. The idea is, though, with piecewise in general, that the formula depends on the value of x. So the formula for the function depends on what value you're trying to plug in. So piecewise functions work where the function changes depending on the value of x, your input. Move over here, some room. The most simple one I can think of, and this is really a really simple one that people introduce piecewise functions with. It's one you deal with, man, you've been dealing with this probably since like 7th grade, 6th, 7th grade. It's the absolute value function. What's the symbol for absolute value? What do you do with that?
Bars.
Yeah, those vertical lines. Okay, so if I say the absolute value of x, what does absolute value do?
The distance away from 0.
Yeah, that's right. And some other people, you said, what's it do? Like more applicably, what do you do with that? If I put a number in there, I say absolute value of 5. What's absolute value of 5?
5.
Okay. And I say absolute value of negative 12, and you tell me it's
12.
Why? What? It's a distance from 0. We're counting over. What does it do? What does it do? Okay, so make everything, be more specific. You actually have to say this in 2 parts, right? Because one of them's already positive. So what does it do? If the number's positive, does it change it?
No.
Okay. If the number's negative, does it change it?
Yes.
So you're telling me that this function does 2 different things depending on what value x is. That's really what you're telling me, right? If x is positive, I leave the number alone. If x is negative, Well, I changed that sign somehow. Does that make sense to you? So really, we can define this as a piecewise function. If we say, okay, f of x is absolute value of x squared, it's really hard to think about that as far as a graph goes. I mean, you might know what the graph looks like, but how would you say, you might have memorized that. Do you know what the graph of absolute value of x looks like?
Looks like a V.
Yeah, show me with your hands how it looks. Don't throw up gang signs. That's all. No, I'm just kidding. No, it's a V. Now, why? How can you get that from this? You can't. You have to either plug in numbers and figure it out, or you have to define it piecewise. Here's how a piecewise definition looks. It has that funny bracket that says all this stuff goes together, and then we have to define it on a piece-by-piece basis. Here's what the absolute value does. It says you're going to do something if x is greater than or equal to 0. You can do something else if x is less than 0. Some people define it as strictly greater than, strictly less than, and then when x equals 0 itself, we're going to define it like this. What do you do if x is bigger than 0? Do you have to change it at all? Now, like this 5, right? You didn't have to change the 5. You just pretty much dropped the absolute value. So we leave the x alone if it's bigger than 0. What do you do if x is less than 0?
Changes.
You say what now?
Negative X.
Okay, so we change the sign. He said negative x. That's when we could change it, right? If I did this and said, how do I get from negative 12 to 12? What math did you do? Magic. I did Harry Potter's my wand. I did magic math. Negative's gone right there. All right, Voldemort, I'll show you who's boss. Too much? What this really says is you have to find some math way to change a sign. The only math way we have to change a sign is either multiply by a negative or divide by a negative. So absolute value of negative 12 really says, follow this formula, and it says you take the negative of negative 12. Does that give you back positive 12? That's the piecewise definition right there. That's it. And it works for anything. You can follow these directions for your piecewise function. It will tell you which part to use. Now, of course, we know this one from a long time ago, but can you see that this is the definition of that? This would do it every time. What's kind of cool is that any piecewise function can be graphed by using their pieces. So we're going to do that next. You can graph any piecewise function by graphing each piece individually. The only thing you have to be concerned about is that you use the appropriate range. That's really it. So we're going to tack on just a little bit. You can graph piecewise functions by graphing each piece individually, but you have to do it for the given range. So we're not going to graph the whole line of f of x equals x. We're just going to do it for a little bit of it. I'm going to use that word domain. Let's give that a try. So here's what we do with graphing piecewise functions. I'll write this out a little bit for you when we get to a more advanced example. But for right now, basically what you do, you ignore one of these functions, one of these pieces, you graph this whole thing and you erase it for the parts that it doesn't actually exist. So right now I want you to think of the line f of x equals x. How does that look? What does f of x equals x look like?
Diagonal.
Sure. You can do it with slope intercept form. What's the intercept?
0.
This is in mx plus b form, yes?
Mm-hmm.
Okay, the plus b, well, that's 0, so we know it's crossing at the origin. What's the slope of that?
1.
So it means it's going up 1 over 1. So if I were to graph this whole thing, this right here is f of x equals x. Agreed? The problem is this right now? The whole thing. Where does it actually exist? And the directions will tell you that. Where does it exist? To the right of the y or to the left of the y? Don't all speak at once. To the right of the y or left of the y? Come on, you gotta be participating here. Yeah, that's because we're looking for the x's that are positive. These x's are negative. It's saying it doesn't exist over here, so we'd erase that part. That doesn't even make sense. So right now we know this is the x, where x is bigger than or equal to 0. That's why we have this closed circle there, because of the equality that includes that little piece. Since we've graphed that piece already, let's go down to the next piece. Negative x just takes that, makes it slope a different way, same intercept. Since we know this already has the piece of a graph, we can't put anything else, otherwise it won't be a function. We're going to leave it just like that. That's where you get your v from. This is the f of x equals negative x. Are you ready to try something just a little bit more advanced? Can we do that? Okay. You guys have any questions on the absolute value? You've all seen that before, yes? Let's see if we can sketch something a little bit funner. Is funner a word? I'm a math teacher. This is funner. I guess I should know words and stuff. That's better. Are you ready? We're going to graph this piece by piece. Now here's a little hint for you. What you want to do, break up the domain first, your x-axis first in the appropriate ranges, graph the pieces, that'll work out for you. So what I'm looking at first is where this starts and stops. I'm looking at the key intervals here. The key intervals are, what's one point that I'm going to have on my graph? Where's the x start and stop?
0.
0's not up there. Don't care about the 0. I care about the -1, because that's where we're going to trade off between one piece and the next piece. Do you get what I'm saying? I want you to find the places where you're switching between functions. One place is at -1, where's the other place?
1.
Sure. Here's what our directions say. Piecewise functions have directions. It says for a certain range that's less than or equal to -1, so everything over here, I'm going to be doing something. Between these two numbers, I'm going to be doing something else. After this number, I'm going to be doing something else. That's how piecewise functions work. Nod your head if you're okay with that. Now we just graph the pieces, making sure we don't overlap these functions, or these intervals. What happens when the x's are less than or equal to -1? What are we doing for this range? So we've already broken it up. We're going to go piece by piece. We're looking at this piece right now. Which of the directions has to do with this piece of information? Is this piece? No, this is bigger than 1. That's the wrong way. Is it this piece? This is between -1 and 1. So we've got to be talking about this piece, and if you look at it, it says x is less or equal to -1. So we know we're this way. What do we have to graph for this piece right here? 0. Wow, what's 0 mean? What's 0 mean?
Horizontal line.
Good. Where? This?
Y equals 0.
This. Which one? This? Do you know? Have I lost you?
The y-axis.
I've lost you? Like this? Have I lost you?
But it'd have to be horizontal, so it'd be like that.
It would have to be horizontal. Listen, if the whole grouping of this kind of confuses you, just write them out differently. Say that you have y equals 0. for a certain bit. Say you have y equals the square root of 1 minus x squared for a certain bit. Say you have y equals x for a certain bit. It's the same thing. You're just grouping all these together in one function and graphing them piece by piece. Do you see that? Okay, so this is the piece that's working where your x is less than -1 or equal to it. This is the piece that's working when you're between -1 and 1. And this is the piece that's working when you're greater than or equal to 1. Split it up if you have to, but you need to be able to graph each of those functions. So, can you all tell me now, what does y equals 0 look like?
The x-axis.
That is the x-axis. Yeah, that's a horizontal line at y equals 0. Y equals a constant, right? We talked about that last time, that it's a horizontal line. So we're talking about this, right there. One question I have for you, should I have an open circle or a closed circle here, and why? And why?
Equal to.
Good. Good, very good. Okay, check. Got it. Let's go to the next piece. The next piece works between -1 and 1. Now, do you also understand why we might have to have no equal sign here, and why if I did this, it would not be a function?
So it'd be overlapping on that
Be
point.
overlapping if these were different. Yeah, that's right. So you're never going to see equals equals. You're always going to for the same value. You're not going to see that. So let's go and see what is that? Oh my gosh, what is that? Do you recognize it? We had it before on the board, except the numbers were a little bit different. What is that? That's circle. If you squared both sides, you get y squared over there, wouldn't you? If you added the x squared, you get x squared plus y squared equals 1. That's a circle. It's centered where, do you think?
The origin.
Origin. Somebody else tell me, what's the radius?
1.
Mm-hmm. That's 1. Guys, if you have questions now would be a good time. Are you okay that this is a circle? How many people feel okay that that's a circle? You can see it. If you can't see it, don't raise your hand. If you can't see it, don't raise your hand. Can you see it? Not so much. If you can't see it, if you're like, oh my gosh, what in the world is that? Square both sides. You get y squared equals 1 minus x squared. If you add the x squared, you get x squared plus y squared equals 1. Now, this isn't, we cheated a little bit. We cheated because this is not an entire circle. An entire circle would be that. You clear? That would give the top half and the bottom half. What are we talking about? The top half or the bottom half? Which one?
Top.
Or just the top half right now. So we want the top half of the circle, centered at 0, 0, with a radius of 1. Well, that looks to me like it's going from here to there. It's going to have an open circle right here, but it's been closed in by the previous function. That's kind of cool, right? We don't have an overlapping point. Is it going to have an open circle or a closed circle here? Yeah. Again, why is it open?
It's not equal to.
Doesn't have that little equals. So we've got our first piece, we got y equals 0. We got our second piece, the top half of the circle, centered at 0, 0, radius 1. The last piece, oh, the last piece, y equals x. How are we going to do that? Y equals x. What's y equals x look like?
It's a line that goes through the origin.
Okay, okay. So normally we would just have a diagonal line, yeah? We've actually already graphed that, it's right here. So if we were to graph that, we'd have this thing. It'd be through the origin, it would go through the point 1, 1, wouldn't it? Because when you plug in 1, you get out 1. So I know that it's going to go through that point, and in fact it's going to be solid because there's an equals there. So if I were to graph it, it would be that diagonal. However, I can't have it exist over here because then this whole thing wouldn't be a function. We're talking about just the piece that's that way. So I'm going to extend that line, erase this piece because I can't have it there. I've already got my piece in the function for that part, that range, that interval. This is the interval we're looking for. That's the piece of the function. Isn't it kind of cool looking? I think it's cool looking. Are you able to understand it? Can you follow? How many feel okay about that one? Good. So piecewise, delineate your. Oh, use that word again. Delineate that x-axis by the appropriate intervals. Graph each piece and you get down. Oh, cool. The last thing we're going to talk about for this section we're going to talk about domain and range. More about domain and range. Hey, when I say domain to you, what do I mean if I talk about the domain?
X values.
More general than just X. What if I'm using different variables? What does domain, someone over here, what does domain mean? Yeah, the inputs. Yeah, you're absolutely right. So when I'm talking about domain, what we mean is all the values you can input into a function. And yeah, you're right, they're usually X's. Typically. Unless you're dealing with like a position function, then you're talking about time. It has to be time. If domain means all the inputs, what does the range mean? These are usually your y values or your f of x or whatever function you're dealing with. Now, in most cases, we have some sort of constraint, in real life especially, we have some sort of constraint on the domain. Let me give you a couple examples on this. Let's say that I give you an example here. The area of a square. The area of a square. Now the domain is all the lengths of the sides of the square that you could plug into this function and get out an appropriate area. Can you tell me if there's any problems with numbers I plug in here? For instance, does S have to be, is S restricted in any way if we're talking about an actual square here?
They are. Both sides.
Oh, the sides do have to be the same, but I'm talking about,
Can't be negative,
why can't it be negative?
because in real life, there is no negative side.
Sure. In the formula, you could plug in -3, couldn't you? It's going to give you 9. But in real life, can you draw me a square right now with the side length of -3? Can you do it? Draw me -3. Oh, you can't do it, right? You're not going to make a square that has, when you measure on a tape measure, it gives you -3. That doesn't happen because we don't measure actual distances in units of length and negatives. So we'd say here, yeah, the area of a square is S squared, but we have a restriction. The side length has to be greater than or equal to 0. You could have a trivial area, trivial square, here it is. That's it, has 0 area, okay, no length of the sides. You can have a 0 length, but you can't have a negative, that's impossible. We also could have some formulaic restraints. Like that one. Like that one, y equals 1 over x. Is there any number I can't plug into that? Sure, why not? Yeah, because your teacher, the first time they showed you a fraction, say, now what number can't you divide by? And you're like, 0. And like, oh, good job, little Johnny, you got it right. Never told you why, right? But you can't divide by 0. Any other number's going to work. Positive, negative, you're fine, but not 0. How about this one? F of x equals the square root of x. Here we couldn't have x equals 0. Can I have x equals 0 there? Can you plug in 0 to a square root?
Yeah.
Well, let me ask you, what's the square root of 0?
0.
Then you can do it. What can't you plug into square roots?
Negative.
Yeah, not inside. So we'd say, sure, this has a restraint where x, it could be equal to 0, but it can't be less than 0. It can't be negative. Otherwise, well, in the real numbers at least. Now let me make a little statement there. If you're talking about complex numbers, can you do it? Sure, yeah, you'd have an I. But if we're talking about real numbers and graphing them on a real number system, well, we can't. You can't do that. Now, what we know is that we're going to redefine domain just a little bit. I don't know if your book does this or not, but how we define we're going to define domain in a special way in this class called the natural domain. The natural domain is basically everything that works in the formula, including the maybe natural restraints of the problem, like at the side length of the square, or the formulaic restraints of like a square root or dividing by 0. So natural domain basically means everything that works in your formula or your function. all values that work in the formula. Would you guys like to do some examples of finding natural domain? Or domain in general? I was hoping you'd say yes. Natural domain asks this question. It says, are there any problems with plugging in numbers, basically? So let's look at a real simple one. We got f of x equals x cubed. It asks, is there anything that you can't plug in, that you can't input into that? Can you think of anything? Can you plug in positives? Can you plug in zero? Can you plug in negatives? Are there any problems you can think of? Can you plug in fractions? Yeah, sure. You can plug in anything you want. If you can plug in anything you want and there's no problems, what we do is we say domain is simply all real numbers. All real numbers. For those of you who like to be very symbolic, you can do it differently. You can say x is an element of the real numbers. That's another way you can say it. So there's no problems there. That says that you can plug in any number within the real numbers and you'll be just fine. How about that one? Can I plug in any number I want to this problem and get something out of it that's reasonable, that's defined? Okay. Can I plug in 0? Yeah. Even though we can't have 0 in the denominator, if I plug it in, well, I'm not getting 0 in the denominator. What numbers can't I plug in? 1. Sure. Now you're doing this in your head, but I want to show you. Here's how you find domain in general. You look for situations where you could have problems. Those situations are roots, square roots specifically, maybe fourth roots, and denominators. To find out what your domain is, really, here's what you're doing in your head. You're saying, I want to make sure that I know that if this denominator is equal to 0, I've got a problem here. Now, the zero product property is going to come up with your answers. It says, I know x minus 1 could possibly equal 0, and give me a problem. I know that x minus 3 could possibly equal 0, and give me a problem. If I solve those, I'm going to get your answers of 1 and 3. Mathematically, that's what you're doing right here. Do you guys see what you're doing? You're saying, I can't plug in 1, I can't plug in 3, because if I do, bam, it's going to give me 0. And even if I multiply by something, it's still going to give me 0, and I know I can't have 0 on the denominator of any fraction. So, by setting a denominator equal to 0, or not equal to 0 is how I used to teach in some other classes, you can do this too. I know it can't be equal to 0, therefore that can't be 0, that can't be 0, and these two things, I cannot have x equal to 0. That's another way you can do it. By setting that equal to 0, solving it down, you find out your problems within your domain for denominators. So here we'd say x is all real numbers except, or but, x does not equal 1 and x does not equal 3. Please don't ignore that does not equal, okay? Because if you do this, I know I just used the equal sign, and that's what a lot of you have been practicing doing for your math careers, but if you do this, except x equals 1 and 3, that says 1 does work. Do you see that? We have to have the not equal to. So once you find those problem numbers, put the not equal to. We're going to find out later that what these things are, if you cannot simplify them out of your function, those are going to be asymptotes, vertical asymptotes. So this is not going to be defined at x equals 1, it's not going to be defined at x equals 3. Those are either going to go up like that. Looks like I'm doing my dance moves. But that's what they're doing. They're going to go up at an infinity, down at infinity, something like that. Do you guys feel okay with this particular domain? Let's try a couple more. I want to get through a few more problems here. Okay, how about this one? How about tan x? Tan x. Is that defined everywhere? Sine goes like this, right? And cosine goes like this. Does tangent go like this? How's tangent go? It makes those kind of weird S's of the snakes all the way down your paper. Why does it do that? Why does it do that? Wasn't rhetorical. Why does it do that? Sure, it's undefined. Why? Why is it undefined at certain points?
Skipping the X value.
Fill this in. You remember how I just told you how functions aren't defined if they have denominators where those denominators equal 0? Well, check it out. If we look at this is tangent, right? If we set this denominator, I'm going to use the not equal to 0 because we know we should not have that equal to 0. If cosine x can't be equal to 0, which is what I'm saying here, what values of cosine make it equal to 0? Where? Do it in terms of radians.
Pi over 2.
Pi over 2 is one of them.
And 3 pi over 2.
So x can't equal, that's why I'm using this right here, x can't equal pi over 2. X can't equal, if you keep on going, you're going to get, let's see, for you guys, here's pi over 2, cosine 0, true? You're going to keep going to 3 pi over 2. If you keep going around the unit circle, you're going to get a lot of different values. It's going to keep repeating both backwards and forwards every pi from that. So pi over 2 plus or minus pi, k pi, where k can be positive or negative integer. It's going to give every part where tangent is not defined because cosine will be 0 at those points. Do you see why this works the way it does? You see why the tangent is not defined at those? Simply because cosine is not defined at those points. You guys see that? Kind of neat, right? It doesn't matter if the numerator is equal to 0. Sine 0 over something, that's defined, that's okay. But something over 0, that's not okay. Okay, last one we're going to talk about, and then we'll call it a day. Do I have any denominators here? Any denominators? Anything over anything? Well, I'm good as far as that goes, but man, I got a square root. So we're going to be having some trouble doing this square root. What do you know about things, the radicand, that's what's inside the radical. What do you know about the radicand of square roots? They have to be, they got to be positive. So when you're dealing with these roots, denominators, I showed you how to do that. What you're going to do is set the denominator equal to 0 or not equal to 0, solve that down. That will give you your problems in natural domain. As far as the radicals go, you know for a fact that this thing is going to have to be bigger than or equal to 0. You know what, we're going to start this next time. I'll show you how to do that. All right, so we're going to continue finding some domains and some ranges of some functions. Now basically, when you're finding what I said was the natural domain, that's just really what works in a function. What we got to do is look for our problem areas. If we can define our problem areas, that really defines what we can plug in and specifically what we can't plug into a function. Really what that comes down to for us is you're always looking for denominators and roots. If you have denominators, you know that at some points you might be undefined. If you have some roots, there might be some ranges of numbers that you can't even plug into your function. So with us up here, we're going to have an issue inside that root. What do you know about square roots? I think we might have talked about this last time. What do you know about those? What numbers can't you have in there?
Negative.
Now, can you plug in a negative here? Yeah, you might be able to, provided that when you work it through the radicand, the inside of your radical, it's positive. That'd be fine. Really what we want, with any root, with any square root, we want the inside part, the radicand, to be greater than, could it be equal to 0? Is that okay to have a root with a 0 inside of it?
Yeah.
Sure, so really we want this. If you remember from last time we had some denominators, what we did was we set our whole denominator equal to 0, or I even use the not equal to 0 because it can't be 0. And you can solve it that way with the equal to 0, finding out your problems. With our roots, what we're going to do is make the inside greater than or equal to 0. We're going to find out those ranges that work. Oh my gosh, that's a quadratic inequality. That's math. See, that's intermediate algebra days for you. How do you do that? What would you do in order to solve that problem?
Factor it.
We would definitely have to factor at least. You probably can see that because it's a quadratic, right? Go ahead and factor that. See what you get. Oh, let's see. I think so. -3, -2, did y'all get that too? Okay, we passed factoring. Whew. Scared if we didn't, my gosh. All right. How do we do the rest of it though?
Set it equal to 0.
If we set each one equal to 0, you know what it's going to tell us? It's going to say that x is greater than or equal to 3, and it's going to say that x is greater than or equal to 2. Do you guys see that? Which actually is not going to be the right thing for us. I know you want to, right? Because you're so ingrained in saying, make this equal to 0, make this equal to 0 by the zero product property. However, we don't have the zero product property because that's not an equation. That's an inequality. If you know how to deal with your inequality, here's what you do. You do find the places where x would equal 0. You kind of temporarily set it equal to 0 in your head. You find those points. Hopefully in your head right now are the points x equals 2 and x equals 3. Do you guys see those points? Here's what you do with this. This is called a basic version of a sign analysis test. So we know that x equals 3 and x equals 2 are some important points for us. Here's what you do with those points. I want you to make up a number line. Put those points in order on your number line. So which one's going to come first for us, going from left to right? Sure. This is basically a graphic representation of your interval, what's going to work in your function here. So notice what we've done. We've said, okay, we know the inside, it's got to be bigger than or equal to 0. We factored it. We have some key points here. We've got x equals 3, x equals 2. We put them on a number line. Now here's how to determine when you're going to be okay in your function and when you're not. If you test a point for each of these intervals, how many intervals do we have? Yeah, it's like you're slicing bread, right? If you have a loaf of bread and you cut it once, you get 2 intervals. If you cut it twice, you get 3 intervals. So you get 3 pieces of bread. Here we have our 3 intervals. If you test each of those intervals with a point in your expression here, it's going to tell you whether it's positive or negative. That's going to tell you what you can plug into your function and what you can't. So let's try this. Can you? And you'll see what I mean after we plug in our first point. Can you tell me what is a point to the left of 2? 0. That's the easiest one to plug in. I want you right now to test 0. So we're going to test 0. Test 0 on the inside of my function. If you plug in 0, how much are you going to get? 6. Wait, positive 6 or negative 6? So would you say that we came up with a positive answer? Yeah, so this is going to be a plus. What that signifies is that every number, try it if you want, every number to the left of 2 is going to give you a positive answer. Are you with me on that? If you tried 1, go for it. You can try it. If you tried any negative number, that's going to give you a positive there. Do you believe me? If you don't, well, just spend the rest of your life trying out numbers, and then you'll come back to me. I believe you when you're like 80 years old and I'm dead. You put it on my epitaph, write me a letter or something. So we've tested every number over here. We know that every one of them is going to be a positive. The reason why we know this, if you think about it, it's a quadratic, right? And you've just found the roots, right? It's actually an upward-facing quadratic. So it goes like this. Positive, 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 dips down at 2. Negative, 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 comes back up at 3. Positive, positive, positive. That's what we're finding out right now. We want the sections that are positive because we know we can only plug in positives, get out positives for a square root. That's the idea. That's what a sign analysis test will do for you. How about a point that's greater than 3? What are you going to try? 5 or 4. Try 5 or 4. The only points you really can't try are 2 and 3. Why? What are 2 and 3 going to give you?
0.
Yeah, that's not going to tell you anything, right? That's not positive or negative. Try 4 right now on your own. Plug that in and see what you get. You can do it in your head if you want. I don't really care about the actual value. All I'm really concerned about is whether you're getting a positive or negative? What'd you get? Yeah, and you should. This is a quadratic, it should alternate. So you tested 4, and you got a plus. Can you give me a point between 2 and 3? Because we got to test a point in there too, just to make sure we have this right. 2.5, great. Try 2.5. Use your calculator if you want. Bet your $1 million is going to be negative. You want to take the bet? No, it's quadratic, right? It's positive here, it's got to be negative there if it crosses the x-axis. So it's going to be a negative. How many people feel okay with what we've done so far? So can you just set this equal to 0 and this equal to 0 and get it right? The answer is no. No, you can't. Because if you did this, watch. If you did x minus 3 is greater than or equal to 0, and you did x minus 2 is greater than or equal to 0, you're going to get x is greater than or equal to 3. That's true. But you're going to get x is greater than or equal to 2. That's wrong. It's not greater than or equal to 2. It's actually less than. Do you see on our graph, this tells you the areas that work, right? It says I can plug in any point over here, and it's going to be okay, because it's going to give me a positive, and positives are okay inside of square root. Some of you are zoning out, you can't zone out right now. This says every number I plug in over here, that's okay, because it's a positive. It's going to get, the inside's going to give me out a positive, and square roots of positives are okay. These numbers aren't so good. Why aren't these numbers good? When I plug them in, the inside part becomes negative. You follow? If we have a square root of a negative, well, that's not so good for real numbers. We can't have that defined. So what this does, it says your domain is all the intervals that actually work. And this is how you can do all of your roots. If you have a function with a root and you're asked to find domain, well, you do this. You set it greater than or equal to 0, and you work it out. Sometimes you might have to do the quadratic with like a basic sign analysis. But this tells you those intervals that actually do work. So take those ones that you know of and write them in interval notation. Can you tell me where this interval starts?
Negative infinity.
Good. And where's it end? So negative infinity all the way up to 2. Now, I know that's got to be a parentheses because infinities always have parentheses. Is this a parentheses or is this a bracket? Why is it a bracket?
Because it's equal to.
Good. It's equal to 0, because if I plugged in the 2, it would give me out 0, right? And that's okay for us. And then to show any other interval, what you do is you put this U standing for a union. I know the 3 is going to work all the way up to positive infinity. That's a different way, and your book likes to do this, a different way to define your domain. Instead of all real numbers except, you use the intervals that you can actually show. So on your book, sometimes instead of saying all real numbers like I showed you last time, they say things like negative infinity to positive infinity. Have you seen that yet? Have you looked through your book? That just means everything. Everything from the far left to the far right. You guys ready to try another one? Did this make sense to you?
Yep.
Okay, cool. Okay, let's go ahead and try to find a natural domain for this. What you ask yourself for domain is, am I going to have any issues? Or basically, do I have one of these situations? Do I have denominators that could possibly equal 0? Or do I have any roots? Do we have any roots here? No, we don't have any roots. That's kind of nice. We don't have to do this whole mess of crap, right? We do have what, though? What's going to be a problem for us? We got a denominator. How we deal with denominators, domain issues with denominators, is we set them equal to, if you want to set equal or not equal to. We know that the x minus 2 can't equal 0. If we do, we're going to get something that's undefined. So right here, the way it is, I know that x minus 2 can't equal 0, which means x can't equal which number? 2. Yeah, that's a problem. So our domain would be all real numbers except x cannot equal 2. You'd have all real numbers but x can't equal 2. That's the deal. Now I want to show you something. This is going to come back later in our class when we deal with continuity. Check this out. True?
Yeah.
Difference of squares. Yes, you can do that. They're factors. True. Can you plug anything into that? If there's no roots and there's no denominators, then yes, you can. Can you plug anything into that? But wait a second. This came from a function that we knew had a problem, didn't it? We knew we could not plug in 2 there. So what's it mean that I can cancel out the problem? Can you actually cancel out a domain problem? Well, that doesn't seem right. And the answer is no, you can't. So even if you can, listen carefully, even if you can simplify your function, which you can here, you still have to keep the original domain. Otherwise, you'd be eliminating some of those problems that you know exist. Did you follow that? I'll say it one more time. If you can simplify your function, do it. But you have to keep the original domain. Because by manipulating your function on this particular case, you've actually eliminated one of your domain problems, which that's not right. You have to keep that original domain. This says you can't plug in 2, right? Just by manipulating it, you can't automatically say, hey, now I can. Harry Potter, here's my math wand. Done. You can't do that. So if you're going to do this simplification, just make a little note that with simplification, you've got to keep your original domain. So our domain stays the same, x still cannot equal 2. So for simplification, keep your original domain. With simplification, keep the original domain. I'd say it to you another way, and this is how I always like to think of it. You can't ever make your domain better by combining or simplifying functions. You can't ever eliminate problems. All you can do is make more problems. So how your functions start, those are the problems you're dealt. That's a hand you're dealt, okay? If you add or subtract functions together or compose them, the only thing you can do is create more problems. You can't eliminate problems. What you start with is what you start with. So if you have a domain right here with this function, that's the domain unless you mess it up even more. Okay? You can't ever make it better by allowing more points. Does that make sense to you? Now, would you like to see what this actually is? Do you want to see what this does? The answer is always yeah.
Yeah.
You see? Oh, okay, good. I hope so. Can you graph this? Can you graph this in your head? Actually, the answer is yeah. These are the same graph. Check it out. This graph right here is, well, that's a y-intercept of 2. Yeah, what's the slope? That means you go up 1, over 1. This is x plus 2. This is the graph of x plus 2 with no domain restrictions. It would say, if I was just given this function and I didn't know about this, that's how I graph it. Now, what this function is, what this one is with your domain issue, it says that you shouldn't be able to plug in the 2, right? If you were able to plug in 2, how much would you get out of it? Plug in 2, how much do you get out of it? Okay, so what happens, what this says is that when I plug in 2, I should be getting out 4. However, I know for a fact from my original function I can't plug in 2 because that would create an undefined situation in my graph. You with me? Don't zone out. You with me still?
Yep.
So it says you can't plug in 2. What that means here is if you can't plug in 2, you can't get out 4. That means you have a hole. And that's what those are. What that is called in the future is called a removable discontinuity. It's not continuous because you have to pick your pencil off the paper, so it's not continuous. However, it's a removable discontinuity, which is defined as if you allow one single point to fill that hole. If you can fill the hole with one single point, it's removable. So that's what we consider that as. So, what are situations in your denominator? There are 2 categories. I'll say them verbally, but I'll go over them more in depth later. If you can cancel out, you know, you love to use those words, cancel out. It's really not a mathy word, but if you can cancel out your domain problem, it's a hole. You with me? It's a hole. If you can't cancel out the domain problem, it's an asymptote. Those are your 2 categories. That makes it kind of simple, doesn't it? If you can cancel out, it's a hole. If you can't cancel out, it's an asymptote. That's it. Let me write that down for you?
Yes.
was hoping I'd get away with something. Let me give you another example before you write that down. I'll give you the same one over here, and I'll give you this one. What can't x equal here? Yeah, that's pretty I gave you a very easy one just so you can see it. Of course, x can't equal 4. Here's the difference. Can you manipulate this to get rid of the x minus 2? Okay, if you cross it out, that means you have a 0 over 0. If you were to plug in the 2, check it out. You're going to get 0 over 0, right? You see that?
Yeah.
When that happens, that means you can cancel it out. You can simplify it out of the problem. That's a whole for you. So when you get 0 over 0, this is a whole. Like that. When you can remove the discontinuity, aka when you can cancel it out of your problem.
Will you
Simplify
always
it out.
get 0 over 0?
If it's a whole, yes.
Okay, so you
Yeah.
use that as a test instead of going through canceling. You just
Sure.
add in whatever number you're not supposed to use, and if it comes to 0,
With polynomials, absolutely.
okay.
With radicals, it'd be very hard to factor that out. Maybe. I don't know. I'll have to do some work on that. I'll get back to you on that one. But with polynomials, absolutely though, because if you plug in a number and it is a 0, that's automatically a root, which means you can factor x minus that number out of your equation. That's math. That's proven. So when you can remove the discontinuity, we've even talked about continuity before, but when you can remove the domain, this means domain problem. That's a whole. That's a whole. 0 over 0 for polynomials. In general, when you can simplify it out of your problem and it's no longer a problem for your domain, that's what we call a whole. It's just a little spot where you don't have a point. Now, if you're okay with the idea of a whole. Okay, now the other thing we got to consider is, well, what happens here? Can you simplify the x minus 4 out of your problem here? Is there any way to factor it and simplify it? If you plug in the 4, do you get 0 over 0? No, you get 12 over 0, and that's an issue, right? That means that you're not going to be able to factor that in any way to be able to simplify that. What this is a vertical asymptote. Vertical asymptote. This happens when you have a number over 0, typically. And it means you can't get rid of the domain issue. I was going to say one more thing, but I forgot it. Those are going to come much later. I'll show you an easy way to do those. We're going to talk about something called limits. All right. Does this outline it better for you? So you're going to have two classifications of domain issues. If you can simplify them out, they're called wholes. If you can't, they're going to be vertical asymptotes. We're going to find out a little bit later on how to determine what happens with those. We'll do another sign analysis test with 4 on our number line. We'll figure out that these asymptotes can either go upwards or downwards, or a combination of those two things. So they'll either be like this, going towards 4 in this case, or like this, going towards 4, or like this. Takes a lot of practice to do that, by the way. It's kind of like rubbing your belly and patting your head. It's hard to do. Can you do that? Let's see. No, I'm just kidding. Camera's not on you guys. I don't care. Okay. Now let's do one more example. We'll go on, two more examples. We'll go on to a word problem, kind of figure out how we can talk about domain with word problems, and then we'll continue on to some trig stuff. So I want us to find the domain and the range of this problem. Find domain and range of that problem. Hey, first thing, are we going to potentially have any problems in this? Any problem? What I'm asking you is basically, are there denominators or are there roots? Are there any of those two things? There's definitely roots, so we potentially could have some problems. We don't have any denominators, so we're not dealing with holes and vertical asymptotes. What we're dealing with is areas of our graph that we can't even plug in a number because it's undefined in the real number system. Do you see the difference there? It's not even defined in those areas. Now, what do you know about the roots? How do we go ahead and find those areas? Set them, they could be equal to 0, right, the inside, or less than 0 or greater than 0? They have to be greater than 0. So what we know is that the 2, is this okay? It doesn't do anything. The only problem we potentially could have is the inside of this root. Because we know if this thing is negative, that's not so good. You okay with that?
Yeah.
Not so good. So we know that whatever we do, whatever we plug in, this has to be greater than or equal to 0. That's a must. Otherwise we come into a serious problem where we're not in the real number system anymore. Can you solve that? How would you solve that, folks? What would you do? Add what? Add 1. This isn't even one of those quadratic inequalities. This is actually a pretty straightforward one. This says you're going to be okay provided x is bigger than or equal to 1. So for our domain, you can say it one of two ways. You can say, okay, the domain is x is bigger than or equal to 1. Or if you want to use the interval notation, which again, you're going to see a lot of answers like that in the back of the book. If you use interval notation, it would say you're going from where to where?
Negative infinity to 1.
Negative infinity to 1. Now that would be x would be less than or equal to 1. We want to be bigger than. 1 to infinity, sure. I know parentheses here. Parentheses or bracket here? Sure. Yeah, very good.
Do you have any preference on which way to write the answer?
I don't care. You're going to see this a lot right now, so you may as well do that. When could you not have it equal to 0 inside a square root? I'm going to change the problem just slightly so you see it. If I erase that and put it over 1, something or 4, any number on the top, this would be the only case for your roots when you wouldn't have this equal to 0. You see, if you actually plug that in, if you plug in your 1, sure, you're going to get 0, but the square root of 0 is
0.
and it's on the denominator. So this would say, oh, wait, yeah, even though that's a square root, I can't have it equal to 0 because if I did, the square root of 0 is still 0, and that's on the denominator of my fraction. See the problem there? Okay. Fraction. That's you. Now, how do you find the range? How do you get range? How do you get something in the range?
It's an output.
It is an output. So, what are wow, that was a sneeze grenade. Oh my. That was a sneeze rocket launcher.
I'm allergic to this stuff.
Allergic to calculus? Me too. I start getting all amped up and excited. Anyway, what are my inputs up here? What can you input? Give me an example that you can input. You can input 1. Give me something else. 3. Someone else give me something. Any real number bigger than or equal to 1, yes? That's everything I can plug in. Now this says what you can get out, right? It says plug in something, you'll get out something. So start with the first number you can plug in, and plug it in. If you plug, what's the first number you can plug in?
1.
Plug in 1. What are you going to get out? You're going to get out what? 2. So this is starting with 2. Now take another number, any number, plug it in and see which way you're going, higher or lower. So pick a number in this domain again, like 3 or 4 or 5. See which way you're going. Where are you going? Pick 2. What's 2 going to give you? Or pick something easier than 2. Pick 10. I don't care what you pick. Pick 5. Pick something like that. Pick 5, okay? What's 5 going to give you? Ah, there you go. Are we getting bigger or smaller than this? So we know that this is going to, as I plug in bigger and bigger numbers towards infinity, this is getting bigger and bigger towards infinity. So my range goes from 2 to infinity. So how do you find range? Well, you plug in your domain. With limits, we're going to find out how to do range a little bit differently. But for right now, you plug in your domain. You still feel okay so far? Yeah? Yes, yes, yes.
Indeed.
Indeed. All right. So let's try one more. We'll go on to our super fun word problem. Are you guys familiar with odd and even functions? Oh boy. Okay. We'll talk about 2 more things then.
Refreshment.
Yeah.
Refreshment.
We want domain and we want range. First things first, let's talk about your domain. Are there going to be any issues with our domain here? Anything that we can't plug in? 1. Oh, what about -1? Is that okay? We'll get 0 over -2. Is that all right to have?
Yeah.
Sure, 0 over a number, that's fine, that's 0. But something over 0, that's not okay. So for our domain, we go, okay, I know that x minus 1 can't equal 0. So x cannot equal 1. Well, that's pretty clear. So the domain is all real numbers except x can equal 1. Now, the question I have for you is that thing a whole or is that thing an asymptote? What do you think? If you don't know, here's how you check. You plug in the number that you're not supposed to be able to plug in. It's like 1. If it gives you 0 over 0, that means you can factor it out if they're polynomials and simplify it out of the problem. If it doesn't give you that, then you can't do that. You can't factor it out. So plug it in, you get 2 over 0. Is that a whole or an asymptote? Definitely an asymptote. So we know we're going to have a vertical asymptote at that point. Yeah, you can't really abbreviate asymptote more than that. You don't want to vert ass. So vert asymptote. That'd be just weird. Anyway, how about the range? How about the range of this thing? That's kind of tough, right? So you don't know what the range is. Well, there is one thing you can do. On certain occasions, this isn't always possible. On certain things, if you can solve it for your x variable, then look at those domain problems for your y, that's actually the range. It's kind of like you're flipping the script on the problem. So you can find the range by solving for the independent variable. That's going to, and then looking at those problems. So if we were to do that, geez, I don't even know if I want to do that. I don't really want to. I guess I will.
You can do it.
I can't. Oh, I know I can.
Such confidence.
I've been doing this a while.
You were in math league in college.
I made fun of the people in math league in college. Actually, it's a horrible person back then. Horrible. Math league is cool. Do math league. It's fun. I swear, it really is. I was too busy with other things to do that. Anyway, do you have problems here? Answer is yes. Yes.
It's the same.
Oh yeah, it is the same. That's just, it's kind of weird that that worked out exactly the same. I did this right, trust me. You can follow it down, this is correct. But now that we've solved for x, if you find the domain for your y's, that's actually the range of your function. Do you see the correlation? It's kind of cool, right? You say, well, if we have any problems on our y's, that means we have problems in our range now. What we're going to get out of the function. What's the problem? What can't you get out?
1.
What's the problem here? What can't you get out of this? You can't get out 1. Because y couldn't equal 1. Do you see how y can't equal 1 here? Yes or no?
Yes.
Okay. So if you do this whole idea backwards and you solve this for your independent variable and you make it so you're kind of like you're finding the domain of your dependent variable, your y here, that's going to give you your range. So our range would say, well now y, I know y cannot equal 1. Can you simplify out this domain issue, which is actually a range issue. Can you simplify out that? Then this is a asymptote as well. Only it's not a vertical asymptote, what is it?
Horizontal.
It's a horizontal asymptote. Now, we're going to have a better way to find horizontal asymptotes in the future because if you haven't noticed, this process, for here, this was really easy. But for every function, can you always solve it for your independent variable? Not even close. No, no, no. That'd be ridiculous. So we're going to have a better way to do that in the future, but for right now, that's how you can find your domain and your range. How many people feel okay with what we talked about so far? All right. You ready for a word problem?
No?
Answer is always
Yes.
yes. You ready for a super fun word problem then?
Sure, why not?
Why not? Come on. You know you're not getting out of it anyway, so you may as well enjoy it.
Wait, does that exist for the word problem?
Yes, it exists. I'll prove it to you right now. It exists.
You just brought it in.
There it is. Look at that.
Your notes.
Here's what we're in the business of. We're in the business of making cardboard boxes. What we're going to do is we're going to take a cardboard box and make it by doing this. Taking your flat piece of cardboard, and we're going to cut out a square here, 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 and here, and then fold up the sides. Will that work to make a box?
Mhm.
We'll use some tape around the sides and be a good-looking box. So very cheap way to make a box. So our box idea is we're going to take a piece of cardboard that is 16 inches by 30 inches, and we're going to make a box by cutting out squares in the corners and folding up the sides. Tell me what you know about the squares.
Same size.
Can the squares be different sizes? You have a really stupid looking box. I mean, you're like, yeah, that's not gonna work so well. So if these aren't the same lengths all the way around, you're not gonna be able to make your actual full flat like shirt box, right? That people like to use for presents. So I know if I call this X, in order to make my nice corner, that's also got to be X, right?
Yeah.
But as soon as we do that, every other corner has to be exactly the same. Otherwise, our box is going to really not be that great, and you're going to get fired from box making. How bad do you have to be to get fired from box making? I mean, come on. No, I'm just kidding. I'm guessing you have to be pretty bad. So we got this piece of cardboard at 16 by 30 inches. We're going to cut out those corners. So we got this machine that's going to come down, and then maybe it indents it here, 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 and here, and we're just going to fold those sides up and crease them. I think what they actually do is they probably just make one cut and then fold the sides over, but you know, we're a little bit more advanced than that. So our box, when we're all said and done, let's see if I can draw this, should look something like this.
You took a 3D drawing class. It's amazing.
Oh no, that should be. That should be. I missed that a little bit.
Never mind.
Yep, never mind. You guys are giving way too much credit. So if I'm folding this up, it's still sitting the same way. It's going to be on this edge. Is this still 16 inches long?
Yeah.
Because what I want to do is I want to find a formula for the volume dependent on X. I want to find a formula for the volume depending on the size of the cut we're making in this cardboard. So find the volume as a function of X. How far is that? Is it still 16 inches?
No.
How much is it?
16 minus 2.
16 minus x. Yes?
16
Whoa,
minus
wait.
2x.
Why 2x?
Because you have to do it from each corner.
Yeah, if we cut both corners and fold that up, we're missing not only one x, but the other x as well. So if I were to find this, yes, I know the maximum length is 16, right? And if I subtract both those cuts, I'm going to get 16 minus 2x. Absolutely. What that means is, how about this length? What's that length?
30 minus
Sure, we still have the same x, right? Because they're squares. So we're going to have 30 minus 2x. What about the depth of our box? How much is the depth of our box?
X.
The depth is x. Okay. How do you find the volume of a rectangular prism like this is?
Weight times width times height.
Say what now?
Weight times width times height.
Makes sense. So as long as we multiply those three dimensions, we'll have the volume. So our volume should be okay. Well, we know that one side is 16 minus 2x. The 2x again comes from the fact that we're cutting out two boxes from each side, or a box from each side, and folding it up. Then we're going to get, well, the length of this is 30 minus 2x, and the depth of this is x. Do you guys feel okay on how to do that? By the way, if you graph that, could you find out an approximate maximum volume if you put that on your graphing calculator? Yeah, if you did, if you work all that out and plug that into your graph, or just plug it in just like that, you're going to get some sort of graph, right? It happens to be a cubic graph. So if you found the maximum height for our domain that we're about to find out, you could find an approximate maximum volume for that. That's kind of neat, right? I think it's neat. Calculators are awesome. Let's talk a little bit, though, about the domain. Are there any issues that we are going to run into with the values of x that we're supposed to plug in? So firstly, we got to check for any denominators. Are there any denominators? Okay, that's okay. That doesn't fail that part. How about roots? Do we have any roots? So we have no issues with that. How about some realistic constraints, though? Is there anything that I'm not supposed to be able to plug in for x? Because I'll tell you, when you put that in a graphic calculator, it's going to go,
negative measurement.
what now?
Negative measurement.
Explain, why not a negative measurement?
You can't measure negative centimeters.
Yeah, I can't tell you. Would you make a box up, please, and put a negative 2-inch cut in it? The box should be bigger. It's imaginary. Can you do that?
Yes.
It's not going to hold very much, right? It'll be flat. Like here, well, yeah. You can't even do it. You can't say make a negative cut out of my piece of paper here. That doesn't make sense. So we know for a fact that x has got to be greater than 0 for sure. Could x equal 0? But could it equal 0? Could you make no cut?
Yeah.
Here's your box. Okay, try to put a package in that. Yeah, it could. It could equal 0 for sure. Is there a maximum cut that we can make for our box? So I know I can't make a negative, but I could make a cut of 1 inch and 2 inches. Is there a maximum to that?
Nothing bigger than 16.
16. Okay, 16. Could I make a cut of 16?
No,
Why not?
because I'd cut off your side.
Would that make a difference?
Yes.
Okay. Let's also, I want you to think about that number for a second. So here's your box, right? And what you're telling me right now is if you have a maximum cut of 16, check this out. This side length is 16, right? You're cutting out two squares, one from the top and one from the bottom. Can I cut out a square of 16 and still cut out a square of 16? Remember, this would be like a square of 2, 4, and 4 would go there. If I take a square of 16, it's the whole thing. That doesn't leave any room for the other square to be cut out of it. Do you get that? That's a problem. So let's rethink that idea. It's not 16 here. We can't do that. What's the maximum length I could cut?
8.
It would be 8. It'd be half that length. Because if I made a cut of 8 here, I made a cut of 8 here, that would be the most I could go without overlapping. If you overlap, you're cutting stuff that's not there anymore. Yes?
But you still wouldn't be able to make a box out of that.
No, you wouldn't, but we weren't able to make a box out of this either. So if we cut 8 and 8, can you take off that whole piece of material? Yeah, your box, and you did it from the other side, your box is going to look like, well, you cut this side off and cut that side off. equal amount, that's now your box. It's a flat piece of paper that's much smaller. You just wasted all your material. But you could do it, right? Again, you'd be fired from box making, but you could do it. And that's our domain. You got to think about these things. Don't just go with the formula. I know we look for two things in the formula. We look for denominators. We also look for roots. But even if those things don't exist, this is a realistic constraint you've got to take into account. If you're dealing with realistic stuff, you've got to really think about, don't let yourself get tripped up by the 16. Really think about what you can and what you can't do with your product. Let you know if you're all right with that. Okay, now I wasn't going to do this, but I'll give you a little refresher on some odd and even functions. Let's talk about odd and even functions for just a little bit. Even functions are functions that have 2s, 4s, 6s, and 8s in them. Well, that's not completely true, but the powers should actually look like that. Odds are usually the 1s, 3s, 5s, 7s. What we say mostly, though, is that even functions are going to be symmetric across the y-axis. Odd functions are symmetric about the origin, which means if you took them and you rotated them 180 degrees about the origin, it's going to make a mirror image with what you have already. So, for even functions, here's what even means, like algebraically or formulaically when you plug something in. Even function says if you plug in a negative number, or if you plug in negative x per se, it's going to give you back out the function just as if you had plugged in the positive version of that number. So if I plug in negative 2 or 2, it says it doesn't matter. That's even. It is symmetric about the y-axis. Now, odd functions say this. It says if you plug in a negative number, it's like taking a function, plugging in the positive of that number, and making it negative. That's what happens with the odd function. It says if I was to plug in negative 2, it'd be like I plugged in positive 2, got the answer, and then made it negative. Do you see the difference between these two things? All right. This is odd. And it's going to be symmetric about the origin. So you can see examples of functions that are even and odd. Well, let's find one out. One each. Well, you guys are asking for the moon today. Here's how you test whether something is even or odd. What you do is you plug in the negative x and you see what happens. So I want to find f of negative x. What that means is that for every place I have an x, I'm now going to put a negative x inside some parentheses. It's like you're composing a couple functions, okay? You're just replacing x with negative x. So that means for this you'd say, I want to see what happens with negative x to the fourth minus negative x squared plus 1. So far, so good? Don't use an actual number. You don't need an actual number. Just use the negative x. It's still going to work out for you. How much is negative x to the fourth? X to the fourth. Because the negative also gets to the fourth power, right? It's going to go away. It's going to become positive. So this is going to become x to the fourth. How much is what's this going to become?
Negative x squared.
So minus x squared and then plus 1. Did we get the same thing back again? Exactly the same thing back again. Yeah. This actually equals f of x. If you plug in the negative x and it gives you back out your original function, your f of x, does that mean it's odd or does that mean it's even? Even. This is definitely an even function. Yeah, and that's how you tell. This is going to be symmetric across the y-axis. Mirror image. Gee, I bet you don't know what this one's going to be. Well, I could trick you, right? I could do you. Let's see, what do I want to do? Yeah, that'll. Again, to check odd or even, you plug in the negative x, you see what happens. So with our problem, we'll have g of negative x. What this says, you're just going to take that negative x and plug it in everywhere you see x. So negative x cubed minus negative x, just like that. Notice negative x cubed, okay, we got it. And the negative x takes that place, that minus is still there regardless of what you plug in, so that has to be there. What happens with this problem?
Sign switch.
Well, yeah, negative x cubed, is that back to our positive x, or do you get a negative x cubed out of that? And this one, yeah, that's for sure, plus. Here's how you tell the odd. If every term in your function is opposite of what you started with, that means what you could do is you could actually factor this out. If you factored a -1, you would actually get, look at that, negative x cubed minus x. Do you see how if I factor out that negative, I'm getting back my x cubed minus x? Yes, no?
Yeah.
This is negative of your original function. This is negative f of x. Negative, that's my original, so I now, oh sorry, I used an f instead of a g. Shame on me. Oh my gosh. I mark you off 2 points for that on a test. I really do, actually, so be careful with that. So if g of x, when I plug in the negative, gives me back negative g of x, that means it's even or odd. What is it? Definitely odd. It'll be symmetric about the origin. Usually S curves are like this. You have a good understanding of the even and odd concept now. Do you feel okay with what we talked about today? Does it all make sense?